Hello, everyone. My name is Lucas. I am one of the engineers here at Semaphore, and today I'm going to be talking to you a little bit about self-hosted agents. We'll look at a few of the details of how things work under the hood, and also discuss a little bit some of the challenges we had to face while developing it. So that's it. Let's get started. So I think it would be helpful for us to start by looking at Semaphore from a distance. And if we do that, we can notice two very distinct parts of Semaphore, the control plane and the agent pool. So the control plane is the brains of the operation, right? It does everything. It orchestrates pipelines, it handles secrets, it receives hooks from the Git providers, has workers to control everything, right? All the logic for Semaphore live in the control plane. And on the other side, we have the agent pool, which is just a group of agents. And the agent is where the Semaphore job actually run. So when you add your commands in the Semaphore YAML, they will eventually end up in the agent and the agent will execute them. Now, since these two parts are quite different, they can run in very different ways. For example, if you're using SaaS with no self-hosted agents, all of these components live inside of our SaaS infrastructure. Now, if you use SaaS with self-hosted agents, you can also use these agents inside of your infrastructure while using the control plane and maybe even some of the cloud agents that we have running on our infrastructure. And with this community and enterprise editions, what you get is both of these parts run inside of your infrastructure. So you have full control over everything. So let's start diving a little bit more on the details of how these two parts talk to each other. First thing we need to understand here is how does the control plane know about the agents? And to understand that, we look at the process we like to call agent registration, which is the first thing that the agent do when it starts. So when you start a new agent, the agent will send a registration request to the control plane. Now, that request needs to be authenticated, so it needs this agent type registration token, which is a token that you get when you create a new agent type. When you go to the UI, you create a new agent type, and the UI will give you this agent type for you to use when starting the agents. Now, when the control plane receives this request, it will run a few checks, and if everything is okay, the new agent will get a new unique agent access token. And from now on, all the requests from the agent will use this access token that is unique to it. So we mentioned that the control plane runs some checks when it receives a new registration request from an agent. And one of those checks happens to make sure that the number of agents that are running at the same time does not go over the limit. We call this limit the organization quota. Now, in this example, the organization quota is 4. So the first 4 agents register just fine, and then the 5th agent is rejected. Now, how does the control plane enforce this? And you might think, well, this is quite simple, right? You just count the number of agents that are currently running. And if the new agent pushes that over the limit, you just reject. And well, yes, that is the answer. We're going to dive in a little bit more into the control plane to understand the common pattern that we use across the entire Semaphore code base to make sure that this number of agents is always below the quota. So let's look a little bit more on the control plane. Up to this point, we have been looking at it as this cloud intelligent piece, but we really didn't look inside of it much. So let's zoom in a little bit more on it. if we zoom in, we're going to see that the control plane is actually a bunch of different services running together and talking to each other, just like a regular microservice architecture. So each service is responsible for its own part of the system, and they all work as a whole to make Semaphore work as expected. What we want here, though, is to look specifically on the service that handles all this communication with the agents, which is the self-hosted hub service. Now, let's zoom in a little bit more again. Here, we can see that the self-hosted hub service is also composed of multiple instances of itself that are running at the same time. This is, again, very common in microservice architectures because this makes it very easy for us to scale up and down and meet the demand and the load that comes from the agent and from the service. But with this architecture, we have one issue. So let's go back to the problem of enforcing the quota. So for every request that the control plane gets, it has to do two things to check the quota, right? The first thing is to count the number of agents running. And then if that number is below the quota, we add the new agent to the pool. The problem here, though, is that these operations are not atomic. So they're not executed as a single unit. So if a bunch of requests for multiple agents come at the same time, we could end up with a situation like this. Here we have a quota of 4, and we currently have 3 agents running. And we have 2 agents here that are sending registration requests at the same time. We can see that one of those requests comes to one of the instances of self-hosted hub, and the other goes to the other one. And since checking the quota and register the agent are not executed atomically, we can't guarantee that one's going to execute, they are going to execute together for the same request, right? So here we can see that actually both checks for quota happen before any of the agents are registered, so they both succeed. And we eventually end up with one agent above the quota, which is a mistake. And how do we fix this? Well, we need to combine those two operations into one single atomic operation. And the way you force that is by using a lock. In our case, if we only had one instance of the self-hosted hub service running, we could use an in-memory lock and call it a day. But here we have multiple instances running, so we can't really do that. And we need to use a distributed lock. In our specific case, we use a Postgres advisory lock. Since the quota is applied on the organization level, we use the organization ID for the lock. So all the requests for the same organization end up using the same lock, which ensure that all of them are executed one after the other atomically. So going back to our example from before, again, our quota of 4 and 3 agents running, we can see that the checking quota and the register operations are grouped together and executed one after the other. So the first one succeeds and the second one doesn't, because it would push the number of agents over the limit. Okay, let's move on a little bit. So now the agent is registered, but what does it do next? So once the agent starts and successfully register with the control plane, it enters the waiting for job state. Now it will remain in this state until a new job is sent to it from the control plane, in which case it's gonna go to the running job state. And again, it will remain on that state until that job is finished. And once the job is finished, it will move to a finished job state. Once it's here, it's going to send an update to the control plane that the job is finished. And then it's either going to disconnect, depending on your configuration, or it's going to go back to the waiting for job state. Now, the agent doesn't transition between these states by itself, the one who actually controls these transitions is the control plane, more specifically the self-hosted hub service. And it does that through what we call the sync protocol. And the sync protocol is just a series of requests, one after the other, separated by an interval that is repeated until the agent disconnects. For example, here's what the sync protocol looks for an ephemeral agent. Now, an ephemeral agent is one that starts, registers itself, and runs a single job only. And after that job finishes, it disconnects. And here we can see how exactly that happens. So it starts by sending a waiting for job state. Um, you know, there's no real job in the queue yet, so the control plane tells it to wait a little bit. And after it sends it again, it receives a command to run the job. And it starts running the job until the job finishes and the agent is told to shut down. Now, here's what the sync protocol looks for a reusable agent. Note that it looks very similar to the ephemeral agent, with the exception that once the agent reports that it finishes the job, the control plane tells it to go back to the waiting for job state. So between one request and the other, there's an interval. How big is that interval? Well, initially we had a fixed interval that was configured on the agent side, but as the number of agents registered started to grow, we realized that there were a few improvements that we could make to more effectively control all this load that comes from the agents. First thing that we realized was that the intervals didn't have to be always the same, right? So we could make them conditional on the agent state. For example, if an agent is waiting for a job, we want that agent to react to a new job entering the queue as quick as possible, right? So in that case, it makes sense for us to use a smaller interval so that that agent starts running that job that is in the queue faster. Another thing we noticed was that we could move this interval logic to the control plane instead of keeping it in the agent. That would give us a little bit more control over certain situations. For example, if the self-hosted hub was having trouble keeping up with all the requests that come from the agents, it could start applying some back pressure to the agents and increase that interval so it has a little bit of a breathing room to recover. Another example here is if we ever want to change this interval logic, having it in the control plane is better because once the new version of the control plane is released, all the agents will start reacting to this change immediately. Instead of, if that was on the agent side, we would need to release a new agent version with this change, wait for everyone to upgrade to the new version, and only then we would see a change in the behavior. Okay, now we understand a little bit better the overall communication between the agent and the control plane. But what about the job execution? We didn't really see how that works, right? We saw the agent goes into this running job state, but how does the user on the job page running the job sees all these job updates that come from the agent? So that is only possible because the agent sends job logs to the control plane while the job is running. So let's look at a little bit of the details for this. Again, here to understand this, we need to zoom in again on the control plane because it's a different service that handles all these job logs updates. And we call that service Log Hub. So the agent sends a bunch of requests to Log Hub while the job is running. Each one of these requests contains a batch of logs, and it is followed by another request containing a more recent batch of logs. And this whole process continues until the job finishes, in which case the agent flushes all the logs that it has for the job that it is running. Okay, let's look more closely at data flow for these job logs while the job is running and also after it finishes. So while the job is running, the agent is sending all these requests to the Log Hub API. The Log Hub API, while the job is running, is appending them to this Redis server. after the job is done, the agent will send a request to the self-hosted hub through the sync protocol to indicate that it finished the job. At that point, the self-hosted hub will send an event to the log hub archivator, which will fetch all the logs for that job in the Redis server, collect them, archive them, and send them to a bucket, which is the final destination for all the job logs. Now, while this is happening, a user using the job page could hit the Log Hub API to fetch the logs for that job, and the Log Hub API will go to Redis and return the logs to the user. Or if the job is done, it will go to the bucket and return to the user. And that is how the job logs go from the agent to the user's browser. Now, one thing we need to do here is to make sure that the Log Hub APIs are not being overused by some job generating a lot of output, because that could cause the Log Hub APIs to become irresponsible to all the other jobs running at that time. And since we can't control really the amount of logs that a job generates, we need to add some protection on the API. So we do that by making the API reject requests after the logs go over a certain size. So here the agent has sent a bunch of requests and has filled all the space that it has for that job. And then after another request that pushes that over the limit, the Log Hub API will return a response saying that it should stop sending logs because it will start rejecting all of those requests now. But what if I really need those huge logs? Maybe I'm debugging something and I need all the logs that I can get. So what then? Do I just lose all those extra logs? Well, no. In this case, the agent will keep collecting the logs in its disk, and then after the job, you can configure it to send all those huge logs to the control plane via a job artifact. Okay, so we talked a lot about the communication between the control plane and the agent. Now let's focus a little bit on the agent. And first things first, the agent is a Golang application that has been open source since 2018. And we compiled that application to several different operating systems and architectures. So you can run that agent pretty much everywhere. You just need to grab the agent binary and the VM, and you're good to go. However, things can get a little bit more complicated than running a single agent, right? For example, you might want a new clean and pristine machine for every job that you run. So that way, one job doesn't interfere with the other jobs that are executing. And if you really need that, then you first need to create one machine with the agent running inside of it, wait for that agent to receive a job, run the job, and finish the job. And after the job is finished, you need to shut down the agent and terminate the VM. And in its place, you need to create a new VM and start this whole process all over again. Another thing you might really want is for your agents to scale up depending on the number of jobs that you have in your queue. For example, if new jobs are created and added to the queue, you want your agent fleet to also increase in size and create new agents to handle all those new jobs that enter the queue. And we also have the other side of this queue, right? The same way that you want the number of agents to increase when the job queue increases, you also want the number of agents to go down when the job queue decreases. So once the job starts finishing and no more jobs are put in the queue, you want the agents to start disconnecting and the machines to be terminated, right? You don't want to overspend on your VMs. Now, all these challenges are handled differently depending on the environment that you are. For example, in AWS, you have a different set of tools than you have in Kubernetes. In AWS, you need to figure out how to build these AMIs that are going to be running these agents, how to configure the outscaling groups so you can make your agent pool bigger or smaller depending on the size of your job queue. You're going to need to figure out how to configure the scripts that start the agent once the instance is created, and also how to terminate the instance once the agent is shut down, so you can rotate the agents for every job. Another thing you need to do is configure IAM roles. to give permissions to the agent and also to the job that the agent is running to manage resources in your environment. And finally, you want to be able to troubleshoot issues. So you need to be pushing logs and metrics to some place that you can monitor. Now, all these tools that we used for AWS don't really exist in Kubernetes. So you need to handle all those problems of agent rotation and scaling them up and down with different tools like Kubernetes deployments or custom controllers or horizontal pod autoscalers. But here we can help you, since all of these issues and challenges have already been addressed by a few additional applications that we developed and maintain that act as this supporting cast to help us handle these challenges for agent management. For example, for AWS, we have this CDK application for deploying the stack, which works for these three Linux, macOS, and Windows operating systems, and all those problems are already solved there. And for Kubernetes, we have this custom controller that already does the same thing and solves all those problems, but for the Kubernetes environment. And this is where we need to wrap things up. Now, we want to continue to make Semaphore easy to run wherever you need to run it. And hopefully now we can do that with the support of the open source community. Thanks for joining me today, and goodbye.